Hello, welcome back. Today we're going to be talking about sequences. A sequence is an ordered list of objects, like red, orange, yellow, green, blue, and purple. We've seen lists before. Remember, lists use parentheses, while sets use curly braces. When we're talking about parts of a sequence, every part of a sequence is called a term. In this course, we make the choice that sequences start with the 0th term. So in this list above, we would say red is the 0th term, orange is the first term, yellow is the second term, green is the third term, blue is the fourth term, and purple is the fifth term. This number, 0, 1, 2, 3, 4, and 5, this number is called the index of the term. I said this was a choice. Yes, this is a choice. We also made a choice earlier in the course about whether 0 is a natural number, and we said yes it is. Other people make the definition that 0 is not a natural number. And other people make a convention that sequences start with term number 1. But in this course, we're making this choice. Sequences start with the 0th term. And so if you're watching other videos or you're reading other books, just be aware of that discrepancy. This choice has some pros and cons. One thing is that this choice can be confusing because of the English language. When you're talking about what is the first term, what we're going to say is the first term corresponds to the term with index 1. Often when we're talking about the indices of a sequence, we'll either use an n or a k. In general, we would look for the nth term of a sequence. Now in this part of the course, our main focus is going to be on sequences that are infinite lists of numbers. Here are 3 examples. 0, 1, 2, 3, 4, ... 0, negative 3, 6, negative 9, 12, ... and 3, 1, 4, 1, 5, 9, ... We could call the first sequence A, and we would write A sub n in parentheses so that we know how to refer to different terms. One way to describe A is that the nth term of A is the number n. Term 0 is 0, term 1 is 1, term 2 is 2, term 3 is 3, etc. And so we could write A sub n is equal to n in order to encapsulate the essence of this sequence. Let's look at this second sequence. This second sequence we'll call B. The way to describe this sequence is that the nth term of B is given by a formula. When n is 0, we plug in, we get 0. When n is 1, we get negative 1 to the 1 times 3 times 1, which gives us negative 3. When n is 2, we plug in, we get negative 1 squared, positive 1 times 6. When n is 3, we get negative 1 cubed times 3, which is negative 9. And so we could write b sub n is equal to negative 1 to the n times 3n. In both of these two examples, the sequences have closed form formulas. That is, there is an explicit formula f of x such that a sub n or b sub n is equal to f of n. We'll be on the lookout for those in the coming videos. Let's look at this last example, the sequence C. Here the description of the sequence is the nth term of C is the nth digit in the decimal representation of pi. Pi is approximately 3.141592 ... And this sequence keeps track of what the different digits are. Now pi is a transcendental number, and there's no good way to write down a formula for what the nth digit of pi is. And so we would say the sequence does not have a closed form formula. A key idea is that a sequence can be thought of as a function. It's a function with domain natural numbers, with some codomain C. And often we'll be dealing with codomain that are integers or codomain that are real numbers. We can see this in two-line notation. The indices are 0, 1, 2, 3, 4, 5, etc. And for sequence B on the previous page, 0 went to 0, 1 went to negative 3, 2 went to 6, 3 went to negative 9, and all those elements are integers. The function A assigns to every natural number n the term a sub n in the codomain. Let's end this video by talking about some common sequences that you may have seen before. Here's the sequence 1, 2, 4, 8, 16. This is the sequence of powers of 2. The nth term is 2 to the n. Sequence B is 0, 1, 4, 9, 16, 25, which are the square numbers. b sub n is equal to n squared. What about 0, 1, 8, 27, 64, 125? Those are the cubed numbers. C sub n is equal to n cubed. Now let's look at sequence D. This one's a little more obscure. Take a second to see if you can figure out the pattern. Let's look at the differences between the different terms. 0 to 0 adds 0. 0 to 1 adds 1. 1 to 3 adds 2. 3 to 6 adds 3. 6 to 10 adds 4. 10 to 15 adds 5. So the next term in this sequence would add 6, would be 21. These are called the triangular numbers, and in this case, d sub n is equal to n choose 2. Here's another sequence you may have seen before. 0, 1, 1, 2, 3, 5, 8, 13, 21, ... When you see those numbers, you think Fibonacci. 0 plus 1 equals 1. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 equals 21. So the next term would be 13 plus 21 equals 34. It's a natural question whether these numbers have a closed form formula, and they do, but it looks a bit different than these other sequences. It's 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. You're not expected to memorize that, but it shows there's always more to learn. Speaking of always more to learn, let's take a look at one more example. Here's the sequence 1, 1, 2, 5, 14, 42, 132, 429, ... In combinatorics, this sequence is just as famous as the Fibonacci sequence, but most people haven't seen it up until this point. It's called the Catalan numbers. When you have a sequence of integers and you're looking for more information about them, you can always go to this website, the Online Encyclopedia of Integer Sequences, to learn more. You type in the terms that you know, you search, and it will tell you all the sequences it has that contain those terms. It's a wonderful resource that was started by Neil Sloan and has blossomed to over 360,000 sequences. It's a fun place to explore. Okay, that's it for this video. See you soon.